Hello and welcome again. We're going to talk about the discrete logarithm problem and Znstar. In the previous videos, we talked about that discrete logarithm problem when this n here is a prime number. We can do that for more general groups, Znstar, where the Znstar has a definition which is going to be similar to the CP star here. Remember, when p is a prime, it's just the collection from 1 to p minus 1. But when n is not a prime, this definition is a little bit different. It's actually going to agree with this here for a prime number. So, and we're going to discuss the discrete logarithm problem here in this group. Alright, first thing we have to do is define what that Znstar is. So this is the definition of Znstar. So if n is bigger than or equal to 1, this collection of elements that we call Znstar is all the elements that are in the list from 1 to n minus 1 that are relatively prime to n. Basically what that means is that the elements that are in here in this list that have no common factors with the number n, or the GCD is equal to 1, which is exactly what I have here. So this is the precise definition of Znstar. It's all the elements that are in this list from 1 through n in such a way that the GCD, or the greatest common divisor between k and n, is equal to 1. Now remember that being GCD equal 1 means exactly that they are relatively prime. It's just another way to say it. It's in mathematical terms, and this is just in plain English. So I'm going to put in this list all the ones that are relatively prime to n. Okay, let's see an example of this. Let's say I want to find all the elements of Z14 star in such a way, of course, that the elements in here satisfy the definition. Okay, so what do we have to do here? So we have to choose from 1 to 14, 1, 2, 3, up to 14. It's up to 14 because this is Z14 star. All the ones that are relatively prime to 14. And I have the list right here. So let's try to understand why this has to be the list. Now, 1 is relatively prime to 14 because 1 and 14 don't have any common factors. 3 and 14 are relatively prime. 3 and 14 that don't have any common factors except for 1, of course. Now 2, you see 2 is not in this list, and 2 is not in this list because 2 and 14 have a common factor, which is 2. So I can say that in here. I can say the GCD, or the greatest common factor between 2 and 14 is, of course, 2 is not equal to 1, so 2 and 14 are not relatively prime, so that's why it's not in this list. 4 is also not in this list because the GCD between 4 and 14 is also 2, so it's not here. 5 is in that list because the GCD between 5 and 14 is 1, and so on. So whatever numbers you don't see here, those numbers will have some common factor other than 1 with 14. So these are the only ones that have only the common factor 1 with 14s, or the relatively prime with 14. So these are all the elements of Z14 star. Okay, just to emphasize, let's look at another one. So let's say I want to find all the elements of Z120 star. So in this case, what I have to do is I have to do this from the list from 1 to 120. So if I have the list of all the elements from 1 to 120, from there I have to select all the ones that are relatively prime to 120, and that's gonna be the elements of this collection here, or this is actually a group. So Z120 star will be this list here. So it's a little bit longer, of course, because I have more elements there, right? So 1, as you can guess, 1 will always be here in Cn star. All of them, because 1 is relatively prime with any natural n. Now 2 is not there, of course, because 2 and 120 have a common factor of 2. 3 is not there for the same reason, and so on. So these are the only numbers that are relatively prime to 120, between 1 and 120. Of course, there are more numbers that are relatively prime to 120, but you have to select the ones that are from this list, from 1 to 120. So these are the only ones I have here so far. So these are the elements of Z120. Now, the reason we are doing that is because we want to look at the discrete logarithm problem in these kinds of groups. They have to be a special kind of not only this one, but a special kind. All right. Now, this is something we talked about earlier with CP star, and we call that a group. And let's recall what a group is. Now, a group basically is a collection of elements that you have. So Zn star is a collection of elements. I have an operation on the elements of that collection, which is in this case that dot that is there is multiplication modulo n, and that operation should satisfy some properties, so I can call this whole thing a group. The first property that is here, number one, it basically says if I take two elements in that collection and Zn star and I operate them with this multiplication modulo n, that result will also be in Zn star, and that is a property of Zn star. That's what we call closed. The second one is if I have three elements, alpha, beta, and gamma, in this collection, then associativity is true. So if I do beta times gamma and then multiply on the left by alpha, that's exactly the same as multiplying alpha and beta and then times gamma. So this operation, dot multiplication modulo n, is associative. Also, the third one is that, of course, if you take 1 and multiply by any number, modulo n, you get back exactly the same number there for any element in Zn star. And this is the one that's probably not the obvious one, is that if you have an element Zn star, you can always find another element in Zn star. So when you multiply those two elements, you get 1. And that is true for every element here in Zn star. Now, we talked about these properties for Zp star with P's prime. Zn star also has these properties, meaning that the Zn star is also a group. All right. Now, we want that group to be cyclic, because in order for us to define what the logarithm problem is, or to define a logarithm problem, we will have to have this guy to be cyclic. Now, that's not entirely true. You can define the logarithm problem in groups that are not cyclic, which I'll explain later. But for the moment, we're going to define those only on groups that are cyclic. And cyclic, remember, means that you have a generator. So I'm going to start. This is the theorem says, if I have a P that is an odd prime number, this group is going to be cyclic. And remember, cyclic means that all the elements of Zn star can be obtained from a power of powers of one single element. So this will be alpha to the 0, alpha to the 1, alpha to the 2, and so on. Now, when is this group cyclic? So this here is the criterion to check whether or not this guy here is cyclic. And the criteria is this. Zn star is going to be cyclic if the number n is equal to 2 or 4. So Z2 star is cyclic, Z4 star is cyclic. Any n that is a power of a prime is also cyclic when this p here is odd number. So for example, 3 cubed, 3 to the 5th, those groups will be cyclic with that n. And also it will be cyclic when the number n looks like 2 times a power of a prime number. And this prime number, remember, has to be odd. So these are the only cases in which that group Zn star that is cyclic. These cases and these cases only. So whatever it doesn't look like this, then it will be cyclic. So let's look at some examples here. So according to that theorem, let's try to check which of these groups that are here are cyclic. So determine which of the following groups are cyclic. How do we know these groups are cyclic? They are cyclic if this n that is here has certain form. It's either 2 for a power of a prime or 2 times the power of a prime number. So basically what I have to do is I have to do the factorization of this and see what kind of number is this. So 148. And remember, what is cyclic? Means that all the elements in here look like powers of one single element. So that's what cyclic means. Okay, let's check 148. So if I have to check 148, the only thing I have to do is factor 148. If you factor it, that's just 2 squared times 37. Now, 2 squared times 37 doesn't look like anything we have here in this list. It's not 2, it's not 4, it's not a power of a prime number, and it's not 2 times the power of a prime number, so therefore that group is not cyclic. So C148 star is not cyclic. Let's look at the next group, this one, Z star 118. So So again, you only look at the number 118 is 2 times 59. It has the form 2 times a power of a prime. In this case, the power, of course, k here is 1, and the prime number is 59. So you have to make sure that the number that is here, of course, is prime number. And therefore, that group is cyclic. And remember, what cyclic means is Z118 star will be powers of an element. All of these elements will be powers of a single element. Let's look at that big number there, 357,111. That number, if you factor it, that's going to be 71 cubed, with 71, of course, being an odd prime number. So that means this number is a power of a prime, a power of an odd prime number. So it has the form p to the k. In this case, the exponent is 3, and the prime, of course, is 71. Because it looks like that, it's a power of a prime, therefore that is a cyclic group. So there must be some element here that when I take powers of that element, it gives me all the elements in that group. So that's basically what cyclic here means. All right. I hope that was clear. Now, if you don't remember what cyclic is, watch the previous videos. I explain a little bit more what cyclic actually means. Now, one thing we want to do here is we want to identify what are the generators of this group, assuming that already I have this to be cyclic. So n here will be 2 for a power of a prime, or 2 times a power of a prime number. When I say prime number here, I mean odd prime number. So what are the generators here? So the generators here are elements of this n star. Of course, they have to be there to be generators, if they satisfy this condition, meaning that when I take that element alpha, whatever the element is here, phi n divided by p. Now, phi n here, if you don't recall that, that's the Euler function, or the number, phi of n is the number of numbers between 1 and n that are relatively prime to n. We already saw how to compute this function here. So that's the Euler function. I take alpha to this divided by p, where p here is a prime divisor of phi n. If that is not congruent to 1 modulo n for all those prime numbers that are divisors of phi n, then this alpha will be a generator. If it is equal to 1, at least for 1 prime, so it won't be a generator. So this is how I check that an alpha is a generator. Now, if you watch the previous videos, you realize that this is very similar to the criteria to check when an element of ZP star with P is prime is a generator. It's exactly the same thing, only that here you have the prime minus 1. All right, so that's the criterion there. Now, let's say now that we want to find all the generators of C54 star. Now, the first thing you have to do, of course, is double check that this is actually a cyclic group. Because if it's not cyclic, there is no point of checking if it has generators. Because if it's not cyclic, it doesn't have any generators at all. So we have to check if this is cyclic first. So let's check that. Z54 star is cyclic. And the reason for that is because if I factor 54, that's going to be equal to 2 times 3 cubed, which is 2 times an odd prime power. And that's enough to say that this group is cyclic. All right. Now, that's not what I want. I want to find all the generators in that group. So to do that, let's first make a list of Z54 star, which is R. Remember, all the elements between 1 and 54 that are relatively prime to 54. If you actually go ahead and check that list, this is the list we have. 1, 5, 7, and so on. All this list that you see here. All right. So as I said here, these are all the numbers from 1 to 54 that are relatively prime to 54. Now, 2 is not there in this list because 2 and 54 have a common factor of 2, so it doesn't have to be here. So that's the definition of Z54 star. Now, to check that something is a generator, we'll have to apply the theorem. And to apply the theorem, there is a couple of things I need to do. First of all, I have to compute phi of n, because I need to compute this modular exponentiation. And the second thing I have to do actually is find what are the prime divisors of phi n here, because I need to check this for all the prime divisors of phi n. So I'm going to compute phi n first. So that's what I'm going to do here. So we're going to compute phi n, and in this case n is 54, so I'm going to have phi of 54. To compute phi n, which is the number of elements from 1 to 54 that are relatively prime to 54, I have to factor 54. So 54, we already factored it because we did it here to check that the group is actually cyclic, which is 2 times 3 cubed. And once you factor like that, this phi distributes as long as these two elements are relatively prime. So 2 and 3 cubed are relatively prime, so it's going to be phi of 2 times phi of 3 cubed. Now, if you don't remember how to do this, you have to go back to the video where I teach this Euler function, which is the number theory for this class. Now, how do you compute phi of 2? If it is a prime number, phi of a prime number is always the prime number minus 1. So that's what I have here, 2 minus 1. If it is a product of a prime number, what you do is you repeat this number 3 cubed here, and then you subtract the same thing, but you subtract 1 from the exponent, so it's 3 squared. So if this here was 3 to the 4th, this will be 3 to the 4 minus 3 cubed. But in this case, it will be 3 cubed minus 3 squared. So I compute that, that's going to be 1, and then times 27 minus 9. And of course, that's going to give you 18. So that's phi of n is 18 there. So phi of 54 is 18. So that's one thing I have to compute. The next thing I have to compute is the prime divisors of 54. So we have to factor 18 just to get the prime divisors. So 18 can be easily factored like this. 18 is equal to 2 times 3 squared. This is 2 times 9. So the prime divisors of 18 are, of course, just 2 and 3. So the only prime divisors that I have there. Now, remember, the reason I'm doing all this, if I scroll all the way up here, is because I have to apply this theorem. I have to know phi n, and I have to know the prime divisors so I can do this exponentiation. Okay, let's go back here to the example. So in this case, let's see. So because I have p equals 2 and p equals 3, what are the exponents I need to use in the congruence? Is phi of n, which is 18 divided by one of the primes, which is 2. That gives me 9. And phi of n divided by the other prime, which is 3. So basically what I have to do is I have to take my element to these powers 9 and 6 and check that it's not congruent to 1 modulo n. And the n in this case is 54. Okay, I want to know all of them, so we have to do exhaustive search. So basically what that means is I have to take all the elements in Z54 star, check every single one of them, and see if they are generators or not. So these are the elements here. I have the list of elements in Z54 star, all the elements from 1 through 53, which are relatively prime to 54. Now, there are a couple of elements that you never check because they will never be generators. 1 is not going to be a generator as long, of course, as this element here is bigger than 3. So it's not going to be a generator there. The last number is going to not be a generator either. So the first one and the last one are things you don't have to check. They will never be generators. So I only have to check 5, 7, 11, and so on, and check if every single one of them is a generator. So this is exhaustive search, probably not the best way to do it, but in this case, this is the only tool we have, so we're gonna go ahead and do it like this, exhaustive search. So I'm gonna start with 5. I have to check if 5 is a generator or not. So I have to take this 5 to these two exponents that I have here, 9 and 6, and check that it's not congruent to 1 modulo 54, and see if they pass the test. So I'm gonna check 5 here. So I take 5 to the exponent, which is 6. That's phi of n divided by p modulo 54. If you do this computation here, this remainder will give you 19, which is not congruent to, which is of course not 1. So that passes the test for that particular prime. I do 5 to the 9th power because the 9 is the other exponent, modulo 54. That gives me 53, and that is not 1. If this happens for all the exponents you have, in this case we only have 2 exponents, 6 and 9, because we only have 2 prime divisors. If you have more, then you of course have to do more of this. If it's never 1, so that means that element is a generator. So 5 is a generator in this case. So and then after that, knowing that 5 is a generator, I go to the next one and check if it is a generator or not. So let's check the next one. So 7 is 7 a generator, so I have to take 7 to the 6th power modulo 54, and that gives me 37, which is not equal to 1. And I do the same for the other exponent, 9, 7 to the 9th power modulo 54, and in this case, unfortunately, that is equal to 1. And whenever you have equal to 1, that's it. The test is not passed, so this is not a generator, so meaning that 7 is not. So 1 is, 7 is not. And then I go down to the list, so 5 is, 7 is not, and I go to 11 and check every single one of them for the criterion that I have for generators. Of course, I'm not going to do this in the video. What I'm going to tell you is the answer. So if you continue like this, checking one by one, you will obtain the list of generators, which are 5, 11, 23, 29, 41, and 47. This will be all the generators of a Z54 star. So these are all the generators of this group here. This group is cyclic. It has more than one generator, so it's 5. It's one of them. So I actually have here 6 generators of this group. So basically what we are doing is applying the criterion to check what the elements of Z54 are generators here. Alright, so I will stop the video now, and in the next video we'll continue with this idea of finding generators for these groups, and I will be able to define for you, hopefully in the next video, what the discrete logarithm problem is in this group here. So I will see you in the next video.